Good afternoon, all. Welcome you all for the post-plan session. So, Professor Barman already introduced yesterday. So, I'm directly convert my room to Professor Barman for his talk. That please you can start, sir.
Thank you. Thank you very much. As all of you know that we have been talking about various applications of nanomagnetism and spintronics in the last lecture, and it's been a little bit slow, so I couldn't finish some of the stuff that I wanted to share in my first part. One of the most important part had been the spin orbit effects in spintronics or spin orbitronics. So as we all know that spin orbit interaction is a relativistic interaction between electron spin and orbital motion. The question is, how does it affect the spintronics property? This paper in 2016 is a nice review paper, which shows various aspects of spin orbit effects in spintronics. So at the center is a spin orbit coupling, and then you can say you have the Rashpa interface, Zielinski-Moria interaction, topological surface states, and then you can go to spin battery, spin logic, skyrmions, new generation memory, SOTM RAM, and so on. So it all has been revolving around the spin orbit coupling. And the spin orbit coupling in a thin film heterostructure can have two different origins. One is, of course, the symmetry independent, which occurs in atomic orbitals, and it is present in all type of crystals. It's pretty much the bulk effect, whereas there is a symmetry dependent part, and that depends on the spatial environment, and it's found in crystal which lacks inversion symmetry. So primarily at the surface and in the interface of thin film heterostructure, and particularly for ferromagnet and heavy metal or ferromagnet non-magnet heterostructure. Heavy metal is required because it has large Z value, which gives you, and because the spin orbit coupling goes as Z to the power 4, so that actually helps in having larger spin orbit interaction. So there are many effects which occurs due to the spin orbit coupling, and I have just listed few effects that I would describe in my talk. One is, of course, the magnetic anisotropy, which is also known as the perpendicular magnetic anisotropy, which is very much dependent on this interaction. Then spin Hall effect, and the inverse of it, the inverse spin Hall effect. You heard about ordinary and anomalous Hall effect. Spin Hall effect is another type of Hall effect which occurs due to the spin orbit effect. Spin pumping effect, I'll describe this, and finally the Zielinski-Moria interaction. So the holy grail or the center of everything is something called a pure spin current. So what is pure spin current? So you can see that here you have two different channels in a sort of ferromagnet having upspin and downspin, and they are flowing into opposite direction. Now they are flowing into opposite direction, so the charge current JE is given by minus E V up plus V down, and because they are flowing into opposite direction, so the vector sum of those will actually cancel out. So you'll not have any charge current, effective charge current flowing through it. However, the pure spin current, which is defined as H cut over 2 V up minus V down, and because their signs are opposite, so actually this will add up and will give rise to a net pure spin current. So this generally occurs in the diffusive regime, but one can show that even in the drift, you can also have a drift current. Okay, so the good thing is that because there is apparently no net flow of charge current, so there are unlike charge current or spin polarized current, it does not dissipate energy as much as you actually get in charge current or spin polarized current. So the energy efficiency is very high because the dissipation, of course, there is a little bit of dissipation, but dissipation is very low, and that is why it is important in high energy efficient memory devices. So when you need to have a spin current, pure spin current, you need to have a battery to produce it. And there are many effects to produce those. Here I have described two of them. One is called the spin Hall effect, another is the spin pumping effect. what is spin Hall effect? So as I showed before, that if you have a heavy metal or non-magnet, it generally does not occur in a ferromagnet. In ferromagnet, you have an anomalous Hall effect. But if you have a non-magnet or heavy metal, so if this spin current, the charge current with two different spins are flowing, then due to some scattering or some intrinsic effect, the spins with two opposite polarization will be split, and they will go into two opposite surface, and they will be accumulated into opposite surface, giving rise to a spin imbalance, and that will give rise to a sort of a gradient and a spin current. On the other hand, if spin current or pure spin current is flowing through this material, then they will actually be deflected in the same direction, and they will give rise to a charge imbalance and will give rise to a charge current. So Diakonov and Perel actually described or discovered this effect in 1971, and they described this effect to have its origin in intrinsic effect, which actually occurs due to the change in the Berry curvature and impurity scatterings, which are from the skew scattering and side jump mechanism. And the spin Hall effect is actually a conversion between charge current and spin current. So this conversion ratio is given by a property or a parameter known as a spin Hall angle. So Js is the spin current is theta sh, sigma is the Pauli spin matrices cross Jc. So Jc is the charge current. So the theta sh gives rise to the spin to charge conversion ratio. And the inverse of it is also defined in a similar manner. So it's very important to have a high spin charge conversion. So high spin Hall angle is very important for spin orbit electronics. The spin pumping effect is actually just the opposite. Here, if you have a ferromagnet adjacent to a non-magnet, and the ferromagnet spin is not in equilibrium, but it is varying. So let's the spin is precessing, then this precessing spin will cause the spin to come to the interface and accumulate here. So you'll have a spin accumulation here, and because of the difference in the chemical potential between these two ferromagnet and non-magnet, it will allow the spin current to carry the angular momentum perpendicular to the magnetization direction. Okay, so the magnetization will, precessing magnetization will allow it to carry the spin angular momentum across this interface, and will cause a pure spin current. And this allows an absorption of angular momentum to the non-magnetic layer, and that will cause a change, actually an increase in the Gilbert damping. So the damping will be faster because this will cause an additional channel for dissipation of the precession. So you can consider this in this way, that the spin pumping is like that. So if you have a kind of a fan rotating, it will give rise to some air drift to in the other room. The spin current is actually analogous to it, whereas here, if some torque comes, some air drift come here, it will start to rotate this turbine. So you can actually draw analogy with this kind of things. So more in spin Hall effect, as the ordinary Hall effect, here you have R0 is equals to mu b, where R0 is the Hall coefficient. In the case of anomalous Hall effect, if you have a magnetic material, you have an additional term, a magnetization dependent term, Ra times m. Whereas in spin Hall effect, you have primarily the spin to charge conversion. So they are quite different actually. Okay, and I already described this this term before. So the origin of these, as I said, there are two main origin. One is the intrinsic effect, which occurs in a 2D electron gas with Raspa spin orbit coupling, and that was given by somebody called Jairo-Senova in this paper. And the extrinsic effects occur due to the impurity scattering. So the intrinsic effect is primarily due to the Berry curvature effect. Here, due to the interband coherence induced by an external electric field, the electron gain an anomalous velocity, and that is orthogonal to the field direction. And depending on the Berry curvature of the conduction electron, it transfers potential, different occurs. So that's the primary reason for this. This is quite prominent in certain material, whereas in material with higher impurity, the impurity scattering will be more important, and the impurity scattering will be of two different types. Of course, one is the skew scattering, another is the side jump. And you can easily see the difference between them. So in the case of skew scattering, it occurs from the impurity in presence of strong spin orbit coupling. And the scattering cross-section depends on the scattering angle and the sign of spin and orbital angular momentum. Whereas in the side jump, there is actually a drift in two different directions. So it's an asymmetric scattering from the impurity potential concerning their relative spin orientation. It results in a spin-dependent lateral shift, actually, of the conduction electron packet. So these are the main origin. And here you can see that they can give rise to two different kinds of torque. So let's say the incident electron with, some spin polarization or, some spin, current is coming. And this is the magnetization. So there will be two different kinds of torque. One is, of course, a torque which is along this direction. And this is the spin transfer torque, which is similar to the damping torque. So you can call this a damping-like torque or anti-damping torque. And another torque will be along this direction. And this is a field-like torque, which is a precession, similar to the precessional torque. Okay, so the outgoing electron will have a direction like that. So you can now modify this Landau-Lipschitz-Gilbert equation. We had written in the last lecture that dm dt was actually minus gamma m cross h effective plus alpha m cross dm dt. So that was the Landau-Lipschitz-Gilbert equation. Now you can add two different torque. One is, of course, the STT-like torque or the damping-like torque, which is actually Js m cross sigma cross m. So this actually is analogous to this torque, Gilbert damping-like torque. And another is the field-like torque, m cross sigma, which is analogous to this. So they will affect these two. So if you actually see how this torque actually affect, we can actually measure the damping and see whether the damping is increasing or decreasing. And from there, the modulation of damping or MOD, that's a delta alpha, we can actually find out the spin Hall angle. Okay, so because the delta alpha is given by h cut gamma Js over 4 EMS sine theta over T pi f. So the Js term actually occurs here. So the spin Hall angle can now be written as theta sh equals to Js over Jc. And you can now write this as delta alpha over Jc. So you can send some charge current. You can see what is the variation in alpha or the delta alpha. And from the other parameters, of course, you can measure their constant. And from there, you can find out the spin Hall angle. So we'll use this method later on to find out the spin Hall angle in various materials. In the case of spin pumping, the Landau-Lipschitz-Gilbert equation will again be modified, but in a slightly different way, because now you have a spin current, additional spin current. So this term is added as gamma 0 over Vms times Is, where Is is a spin current, and it can have different components. Of course, the Is0, which is the DC spin current, and then you have the pumped spin current, Is pump plus Is back. That means there can also be a backflow of the spin current back to the ferromagnet. Okay, so here again, there will be a modulation of damping because of that. And here delta alpha is not similar to that, but it has a different form. And it is now given by, of course, G mu B GR over 4 pi MSD, where GR is the spin pumping coefficient, D is the ferromagnetic layer thickness, and 1 minus e to the power minus 2t over lambda. And this T is the heavy metal layer thickness, and lambda is called the spin diffusion length. That means, the length over which it can actually be, traversing before it actually decay. So it's you can call it a decay length of the pure spin current inside the non-magnet. So this is the spin diffusion length, and the value of this actually varies quite significantly from material to material. So then there is another important term which is called the spin mixing conductance, because it is happening across two interface. So their conductance mixing is very important, and this spin mixing conductance can be found out from a term like that, where again this 1 minus 2t over lambda is there. So this is called the effective spin mixing conductance, because there can also be a backflow of spin from the non-magnet to the ferromagnet. And that backflow factor is given by a term like that, where epsilon is called the spin flip probability parameter, which is very important parameter. And then the spin mixing, the intrinsic spin mixing conductance is given by this term. So this is very important for a certain heterostructure. This value will determine how much the spin will be transported from one material to from the ferromagnet to non-magnet, because not only the generation but the transport will be important for the effective use of this pure spin current, because you can generate a lot of pure spin current, but if you cannot transport it efficiently, it will not be useful. So this interfacial spin transparency actually determines that, which determine the amount of spin transport, and which is found out from a term like that, and we can actually find this by doing all this measurement and analysis. So that is our goal, that what would be the interface transparency. So if we know that what is the spin Hall angle and what is the interface spin transparency, we can then say that for a certain heterostructure, this amount of spin current can be generated and transported. So so then we have this another way of measuring it, which is called the spin torque ferromagnetic resonance. Here you can actually have a non-magnet and ferromagnet, and if we apply an RF current, then this the RF current will produce an Oersted field, and that will cause the ferromagnet spin to precess, and the non-magnet will also have a current, a spin current generated in it, and so the Oersted field will create an asymmetric FMR, whereas the spin current from here to here will give you a symmetric FMR. So if you measure the anisotropic magnetoresistance here, that will actually cause an oscillating electric resistance, and this oscillating electric resistance actually give rise to an along with this it produces a DC voltage. This is called a spin torque diode effect. So this is a very important effect, and from there also one can measure the spin to charge conversion efficiency. Similarly, from the modulation of damping, as I mentioned before, one can do that, but here you need an RF and DC component of current. So this is the measurement procedure. So you will have a a ferromagnet and non-magnet heterostructure, and because you want to deal with both the DC and RF current, so you need to have a LC kind of circuit, which is called a bias T. Of course, as you know that the AC component will be flowing very easily through the capacitor, where the DC component can be measured very easily through the inductor. So you can apply the AC component through this and measure the DC voltage by the inductor part. So that's that. So I will skip the fabrication part because I don't have much time. I will actually go into some of the example results that I want to show you. So for that, I probably have to stop sharing and change my slide. Can you see my slides now? This slide?
Yes, sir.
Okay.
Yes, sir.
Okay, thank you. So here I will show you some example results that I have been talking a lot about various theory and measurement technique and all this, but without showing some results, it will not be complete. So let me one by one try to show. So first thing I will study is I'll start from the fastest process, the ultrafast demagnetization, which occurs in the femtosecond time scale. And then I will go into the precessional dynamics, and there I will try to show how it can be used to measure the spin Hall angle, spin pumping, and the spin wave can be used to measure the interfacial DMI. And then I will try to give you some example of some of the magnonic crystals and so on. Let me see how much I can do. Okay, so ultrafast demagnetization in magnetic multilayers I will do. And it has a long history. It's a very rich physics. So in 1996, actually, Barman et al. Showed that a nickel foil by incident, and if you incident a femtosecond laser on it, it can be demagnetized in presence of a ferromagnet. A ferromagnet in presence of a magnetic field can be partially or fully demagnetized. So this actually opened up a new physics because there's a lot of interesting physics involved, and at the same time, one can do all optical writing using this. Okay, because if you can demagnetize and remagnetize again, you can actually do the writing part at a femtosecond time scale. Okay, so then he actually used this something called 3-temperature model to understand this, where the electron lattice and the spin temperature and spin degree of freedom become in non-equilibrium with each other, and they interact, and you can see how the temperatures or the energy of the three systems, the electron lattice, spin and lattice temperature actually vary. You can see that the electron temperature actually rises very fast, follows by the spin temperature. It lags a little bit, and after a pretty long time, the lattice temperature start to grow. So when the lattice heats up, it's the physical heating of the system. But before that, you can call it a non-thermal effect because the physical heating didn't take place by that time. So then there have been a lot of debate about the explanation of that, and two different classes of explanation came up. One is called the spin flip scattering, and one is this Elliott-Yaffe-like or phonon-mediated spin flip scattering, or Magnon, Coulomb exchange, relativistic phonon-mediated, and a lot of interesting physics came up. The other class of people start to say that, of course, there can be contribution from spin current or super diffusive spin current, where the laser excited hot electrons, they play a crucial role in channeling energy from the system and causing the ultrafast demagnetization through spin dependent transport. Or there can also be a thermal transport or heat current. All of those actually take place in the femtosecond or sub-picosecond time scale. So super diffusive spin current has been a very debatable and hot topic during last 10 years or so. And here one example was shown in nickel aluminum system. And here the laser excited electrons in SP bands of high velocity, and they excite the spin majority and minority electron bands with different lifetimes, and that causes a depletion of majority carrier. And here the spin current actually flows in a super diffusive manner, which is nothing but it starts in a ballistic way. So we know that the diffusion equation is given by the mean square displacement is proportional to the T to the power gamma, where gamma, the parameter, if it is 2, then it is ballistic regime, and if it is 1, it is called a diffusive regime. In this case, it's actually between 1 and 2 because it starts with 2 and slowly goes into the diffusive regime. So that is why it is called the super diffusive spin current. And more recently, another theory came up where optically induced spin transfer effect has been caused. Considered to be the primary effect for multi-sublattice alloys and multilayers. So it's a very, very rich field, involved. So we studied these magnetic multilayers with perpendicular magnetic anisotropy, and this is also a very interesting system. And this also has a long history because it's a result of magnetic anisotropy at the interface, originated from the lower symmetry. So basically broken inversion symmetry at the surface and interface, and was proposed by Neal in 1954. But there is more to it, and one has shown that if you have a ferromagnet non-magnet, and if you start changing the thickness of the ferromagnetic layer, in this case, let's say cobalt, and you can see that at a critical the order of about 10 angstrom, and if you are above that, if you are in the in-plane orientation, you have in-plane anisotropy. And if you go to thickness below that, then if you slowly go into the out of plane or the perpendicularly magnetized direction, or perpendicular anisotropy. And you can consider this, the effective anisotropy, to have a volume term, KV, and a surface term, which is inversely proportional to the thickness. And this, this T perpendicular, or the critical thickness, is given by 2Ks over KV. Then you have the XMCD measurement at the cobalt L23 and M23 core edges, and that reveals a strongly enhanced perpendicular cobalt orbital magnetic moment. So that was also considered to be important for this perpendicular anisotropy in cobalt platinum, multilayer. So and people started to believe that there is a hybridization of the cobalt 3D and the platinum 5D band, and that is actually persists for the thinnest cobalt layer. So, that was, that. And then the importance of this material is, of course, in various kinds of, perpendicular media and so on, but more in the spin transfer torque MRAM or the STT MRAM devices, because here the right current, I showed you that how the, MRAM works. So you have a right current and read current, and also you need to have a thermal stability. So you want to have, and the problem was that as you're reducing the bit size, the anisotropy increases and the right current actually increases. So you can see that JC, that is the right current, is proportional to alpha, that is Gilbert damping, times MS, the saturation magnetization, times the anisotropy. So it's indeed proportional to the anisotropy. And you have a thermal stability, which is proportional to MS and HK. So of course, you need to have a high thermal stability. So for that, MS and HK should be high, but you need to reduce the right current. But here MS, HK are also there. So the only hope is that if you have a small value of alpha. So if you have a small alpha and high MS and HK, that is the ideal material for this STT MRAM device. So a correlation at the same time, alpha, that is Gilbert damping, which is also occurs from the spin orbit coupling, HK, which is also a spin orbit coupling mediated term, anisotropy, they should be correlated. So one needs to find out a correlation between these. So all these are very interesting topics. So we did this, study. I mean, actually started long back, more than 10 years back, and we had this cobalt palladium multilayer. Here, cobalt thickness T actually is varied from 0.7 to 10 angstrom in one series, keeping n equals to 8. And in another series, we actually kept T equals to 2.8 angstrom, and then we varied the number of bilayer repeats. Okay, so these are two different set of samples. And here some example cross-sectional TEM, which showed that they're very nicely, staggered planes and all. And X-ray reflectivity also gives rise to measured thicknesses within plus minus 5% of the nominal thickness, and average roughness is also very good. So the interface is very clean. And we did the measurement. These are the static MOKE measurement, which shows the magnetic hysteresis loop of samples with varying cobalt layer thickness. And you can see that it goes from a square loop to very strange looking loop, and then finally a hard axis like loop. And we did all the analysis to find out the anisotropy. We showed you how we can measure the extract the anisotropy from the hysteresis loop. And we plotted the anisotropy, and we see that the anisotropy is fairly low, although it is still perpendicular, and it actually increases to a high value to about T equals to 0.22 angstrom, and below which it actually drops very fast. So we know that about 0.2 angstrom, is actually a value where so it's 2.2 angstrom, so 0.22 nanometer. It's actually the monolayer thickness. Okay, so below that, when you go to below a monolayer thickness, you will not have a continuous growth. You will have island formation. Okay, and as a result, the interface will not be continuous. Interface will be kind of patches. Interface will have patches, and as a result, the anisotropy will decrease. So this is what we understand from here. And then we do the ultrafast demagnetization measurement by using the time resolved magnetoptical current. And first thing we measured is the ultrafast demagnetization. So here you can see that in presence of a magnetic field, the sample actually demagnetizes within sort of 100 of femtosecond time scale. And these are the data for different values of the cobalt layer thickness. And how we model it, there is 3 temperature model I showed you, and this 3 temperature model is actually a rate equations where you have the coupling between electron lattice and spin bath. So there are 3 different coupled differential equation, but we will not solve it right now. First thing we'll do is try to find out the value of the demagnetization or the time of the demagnetization. For that, we actually linearize it, and we extract a sort of an expression which is still very complicated, but we can fit this expression with that. And after a lot of effort, we can fit it pretty nicely, and we can find out two different parameters. One is tau m, which is the demagnetization time. Another is tau e, which is the first relaxation time. So you can see that tau m, that is the demagnetization, is a purple symbol, and it actually increases up to 0.22 nanometer, and then it decreases. So it actually follows somewhat the anisotropy trend. But it will not, I will show you that it is not due to the anisotropy or the spin orbit coupling, but there are more to it. And of course, the relaxation time is fairly flat. So then what we do is we do the fluence dependence. So we can change the pump leisure fluence. And when we do that, we see that they actually vary linearly. So the demagnetization time changes from about 200 femtosecond to value pretty high. But it still does not affect the trend of demagnetization time with thickness. So you can see they actually, all of them still show the increase and a maximum at around 0.22 nanometer and then a decrease. So what happens here? So this is the kind of initial qualitative understanding that as TCO or the cobalt layer thickness decreases, more discontinuities and defects are introduced at the cobalt palladium interface. And that can enhance the phonon-mediated spin flip scattering time, and maybe the tau m. But the declining nature, if that was the case, then why then it still decreases again, below 0.22 nanometer? So that is ruled out, because if that was only the defect and discontinuities were the case, then it should have continued to increase even below 0.2 nanometer. So that is not the case. Then I said the role of PMA, whether the anisotropy has any role, but anisotropy value is of the order of only 1 millielectron volt, whereas this is strongly enhanced by the exchange interaction, which has an electron volt energy. So that cannot actually cause a change in the demagnetization. Then what is left is the role of cobalt layer dependent Curie temperature in the ultra 3 regime, and also the electron temperature. So we'll see whether it has any significant influence on the ultrafast demagnetization process. But then measurement of Curie temperature of ultra thin film is extremely difficult. It requires a lot of effort. So we actually did that. To accomplish this task, we actually measured the change in the remnant magnetic moment as a function of temperature. Okay, so we actually measured the hysteresis loop at every temperature and rebuilt the sort of temperature dependent magnetization. And these are the curves, and all of those took a long time to measure. And from here we are able to find out the Curie temperature very precisely. And this is the Curie temperature versus TCO, and you can see that it actually decreases like that. So below a critical thickness, cobalt layer form a ferromagnetic cobalt island, and between the PD layer, and that reduces the long range interaction, as well as the coordination number of each ferromagnetic atom, and that leads to a ill-defined TC. So we do not measure it below 0.22 nanometer. So the question is there any role of the electron temperature also? So for that, we have to find out the electron temperature. So how do we do that? We now have to model it with the full 3 temperature model. Earlier, we only modeled with this expression, but now we will model it with this. So that requires, again, a lot of effort, because solving this 3 coupled differential equation is not easy. I think we are the only people in India can do that at the moment. And then we did that. We did this modeling, and from here we are able to find out the temperatures, 3 different temperature, the electron spin and lattice temperature. And you can see this is the electron temperature, and it actually goes well beyond 2500 Kelvin, the electron temperature. So whereas the spin temperature actually goes beyond about 500 Kelvin, lattice temperature actually doesn't increase much. So you can see that even though electron temperature is going beyond 2500 Kelvin, the sample is unaffected. Sample doesn't burn because the lattice temperature is very low. Okay, so that clearly shows that it is a non-thermal process. And we plot the electron temperature as a function of delay time for all these 4 different samples that we measured the Curie temperature for, and they all show a similar variation with a change in the amplitude. So then we plot the T over Tc, the electron and Curie temperature ratio, which now shows a very similar trend as the demagnetization time. So variation of demagnetization time with thickness has exactly the same trend as T over Tc. And in microscopic 3-temperature model, the T over Tc appears very clearly. So we can now correlate the tau m with T and Tc, and it shows a nearly linear correlation. So this declining nature of T and Tc with TCO resembles the variation of tau m. In other words, TCO decreases the difference between the T and Tc, and it continues to increase the increase and enhances the tau m continuously. So that was for that sample, in the ultra thin regime, and then we want to see that if there are other effects in addition to the spin flip scattering and the role of electron Curie temperature, if there are other effects to the demagnetization. For that, we actually would like to change the number of bilayer repeat, and we'll see that whether this can the spin flip and non-spin flip processes coexist in the same material or same system. So we took this system and we varied n, the number of bilayer repeat, from 2 to 125. So it goes from a very thin, rather thin sample to rather thick sample. The cobalt layer thickness is not varied, but the overall thickness of the stack will be varied. So we did the ultra-fast demagnetization measurement again, and here is the data, and here you can see that this is for n equals to 2, and we are increasing the fluence along this direction. But in all cases, there is a single step demagnetization. We are increasing n to 4, 8, still the same. But when you come to n equals to 20, let's say, you start to see that this thing is not going to remagnetize similar to this. When we come to n equals to 50, we see that the demagnetization doesn't stop here, but it continues to demagnetize at a slow rate. So this is called the type 2 demagnetization. In addition to the type 1, there is a type 2 demagnetization. And the same trend is observed in n equals to 125 also. So if we now plot them for the same fluence in the same plot, then you can see that from n equals to 4 to n equals to 50, for example, it go from a single step demagnetization to a 2-step demagnetization. And if you do this 3-temperature modeling and find out the demagnetization time, you can see that for n equals to 4, 8, and 20, it slowly decreases as usual. But for n equals to 50, there is a very sharp increase, and in the demag time, because of the 2 different type of demagnetization, the slower component actually increases the demagnetization to about a picosecond. So from femtosecond, it goes to about a picosecond. And we try to understand this behavior. And from this model, so we generated a model that you have in addition to the direct interaction, which is like here, you have the pump and probe, which this is the purple line or the blue curve is the pump. So this is the 400 nanometer, whereas the red one is the probe, which is 800 nanometer. So here, both of them actually penetrate down to the same volume. And so you are actually measuring the uniformly excited region of the sample. So here you have only the direct excitation. But in this case, when you go to n equals to 50, so in addition to this direct excitation, you will also have an indirect excitation. So in this region, the probe beam still penetrates, but the pump beam doesn't penetrate. So the demagnetization is still happening here because of the transport of thermal current and spin current from the top part, the directly excited part. This is our sort of hand waving or the qualitative understanding first. But we didn't stop here. We did control experiment. So what did we do? We now changed the pump beam wavelength. So we had an optical parametric amplifier. From here, we can actually vary the wavelength, do the pump experiment all over again. So that takes a long time, but we did this experiment. And here you can see that when we are in the 480 nanometer or something, which is similar to 400 nanometer, you still have this 2-step demagnetization. And slowly you are increasing the pump wavelength, and at around 600 nanometer, you slowly go into the one-step demagnetization, and at around 690 nanometer, you are going to the single-step demagnetization. Because from here to here, you slowly, from here to here, you go from this range to this range. So 690 nanometer will actually penetrate almost to this part. Okay, so you will have nearly direct excitation, and that is why no indirect excitation will take place, and as a result, you have this single-step demagnetization. So these are two important developments that we had in the last few years in the ultrafast demagnetization, and then we go to the precessional dynamics. As I said, that beyond the ultrafast demagnetization and relaxation, there is a oscillation, damped oscillation, which is the precessional dynamics. And we'll do this measurement here. For the cobalt palladium sample only we start with, and we did this thickness dependent measurement. And here you can see that the damping, not only the precession frequency, the precession frequency is very fast here, and but it actually increases, and the damping also changes. So from 1 nanometer to 0.22 nanometer, you see the precession frequency goes from few gigahertz to nearly 100 gigahertz. So 100 gigahertz means 0.1 terahertz. So it's very, very high frequency. But let's see what is the damping, because we can clearly see that the line width changes. The line width also gives rise to damping, but we actually measure the damping in a different way. We fit this time-dependent curve with this kind of expression, and we find the decay time, and by fitting it with this expression where the damping also appear, we could find out the damping. And at the same time, we do the field variation, frequency versus field, and model with equation like that. And from here, we find out the anisotropy. Anisotropy is here, effective anisotropy. So we did that, and we find out that this damping is actually varying very linearly with the inverse of the cobalt layer thickness, which shows that there is either spin pumping or hybridization or some kind of effect here. And let's see how it varies with K effective. So we see in the beginning, I said that there should be a correlation. We predicted there should be a correlation between alpha and the anisotropy. And here we experimentally found from all these rigorous experiments that yes, the damping and anisotropy actually are correlated. And here we can see that for about this regime, okay, significantly high anisotropy. Okay, even this one can be used. So fairly low damping and high anisotropy. So this can be used for STT-MRAM. But in order to understand this behavior, we did more sort of analysis. And we find that the magnon-magnon scattering is not applicable, because this is applicable only for in-plane magnetized sample. Because this is perpendicularly magnetized, this is not applicable here. We also calculated the spin pumping related phenomena, and we found that the spin pumping is negligible here also. So the roughness and alloying will have opposite effect. So this is also ruled out. And finally, we find out that the interfacial hybridization of 3D and 4D bands of cobalt and palladium are actually responsible for this. And because alpha and anisotropy both have their origin in the spin orbit interaction, and they are approximately proportional to xi square over W. Xi is the spin orbit interaction, and W is the D bandwidth. Okay, so and that is why they are correlated. So this correlation have been established. So now I'll show you how the spin Hall effect and spin Hall angle can be measured. Okay. So as I said that we can measure this by using something called an all-optical technique. And here we have a ferromagnet and heavy metal. So far, they have been measured by using electrical technique, which has different kinds of problems. And they were reporting values of spin Hall angle over a broad range. So even for platinum, the value actually varied by 2 orders of magnitude. There was no kind of correlation between different values. So we wanted to develop a very robust and reliable technique and an all-optical non-invasive technique. And what we did is like that. So we deposited a heavy metal and a ferromagnet bilayer, and we created a contact pad for flowing current, DC current through the heavy metal, and of course some will be flowing through the ferromagnet as well. And instead of measuring any resistance or anything like that, we will do the all optical measurement of precession. So what will happen when the current will flow through the heavy metal, because of the spin Hall effect, it will split into two opposite spin, and that will give rise to a spin current, and the spin current will be injected into the ferromagnet. And now what I will do is I will excite the precessional dynamics in this sample. And as I said, that this spin current will exert a damping like torque or an anti-damping like torque, and that torque will act collinearly with the damping torque. So here damping torque is along that direction. So the anti-damping torque will be collinear, either parallel or anti-parallel to it. So that will change the damping, and depending on the direction of the charge current, whether it is in this direction or other direction, it will either increase or decrease the damping. So that is the experiment I would do, and then I have shown you this modeling. We'll find out the spin Hall angle. Let's see if we can do that. So this is car rotation as a function of time, and this is the precessional part. So here the precessional part can be used to measure the damping, and here I'm varying the charge current, not only the magnitude but also its direction. So in this panel, these are negative charge current. In this panel, they are positive charge current, and the magnitude is also decreasing from 10 to the 10 ampere here, and slowly it's going to 10 to the 9 and down to 0. And we can clearly see that the damping value is changing, although the damping value should not change by that much, but it is still changing significantly here too. And what we did is, before doing the alpha versus JC, we want to see that whether the damping is intrinsic or extrinsic in nature. So we plot the damping as a function of frequency, and it is flat. So that tells me that the damping is intrinsic in nature. And then I plotted alpha as a function of the charge current. And you can see that for zero charge current, this is the intrinsic damping. And theta equals to 0 degree, that is flat. But when I'm varying the value of theta, this is the bias field angle basically. So theta is this angle, the bias field angle. And here I can see that the damping is varying asymmetrically with respect to sort of charge current axis. So basically, for the positive charge current, the damping is decreasing, whereas for the negative charge current, the damping is increasing. Okay. So from this modulation of damping, and by doing all the modeling, we were able to find the delta alpha over JC, and we found that the linear modulation of damping is about plus minus 7%, and that gives me a spin Hall angle of 0.11. That means an 11% conversion from spin to charge current or charge to spin current. So that is a reliable value for platinum, because some of the reliable measurements showed that the value between 0.1 to 0.15. So our value falls in that. So when we are confident about that, we went on to measure the spin Hall angle in a very important material, that is tungsten. So platinum is very expensive material. Okay. And platinum can also give rise to the perpendicular magnetic anisotropy. But there are other heavy metals like tungsten and tantalum, which can be rather cost effective, and they do not easily give rise to perpendicular anisotropy. So we want to see whether they can give rise to a good value or better value sometime. Okay. So in order to, but tungsten has a problem that it actually has a phase change from beta phase to alpha phase. Beta is the BCC phase, sorry, A15 phase, and alpha is the BCC phase. So there can be a problem there actually. So let's see what happens. So we did this experiment where we varied the this is not tantalum, but this is tungsten. We also had tantalum, but by mistake I put the this here. So tungsten and cobalt iron boron. So cobalt iron boron is fixed at 3 nanometer, and tungsten is varied from 2 to 7 nanometer. And the first thing is we did the XRD measurement, where we can see that there is a phase change from beta to mixed beta and alpha phase as we are going from about 5 to 6 nanometer. because this beta phase slowly disappear and the alpha phase actually is prominent at around 6 nanometer. From the resistivity measurement also, we see there is a transition from beta to alpha dominated phase. So we want to see that how the spin Hall angle varies there. So we did this damping measurement here, and here is the modulation of damping measurement. So here we are varying the charge current density, its value and strength and orientation. And this is alpha as a function of JC. And this is the modulation of damping. We do all the modeling as we did before. And we got a modulation of damping up to 0.15%, which is pretty large. And from here, we've calculated the spin Hall angle. And spin Hall angle turned out to be a giant spin Hall angle of about 40% for tungsten and cobalt iron boron. And this value actually persists for about 2 or 3 value of thickness. But when we actually goes into the alpha phase, the value drastically reduces to a very low value. So some structural changes occur, which causes this interface to change. And as a result, the value decreases. On this side, the value also decreases a little bit, but this is because of the backflow effect. In any case, the field-like torque or the other Joule heating effect can be found out from the frequency versus the current. Okay, so that was the spin Hall angle. So we found out that tungsten gives rise to a very high spin Hall angle. And now we try to see what would be the interface spin transparency. And for that, we'll do the spin pumping experiment. We know that the spin pumping is an effect where you have if you induce a precessional dynamics in a ferromagnet, the adjacent non-magnet will have the spin angular momentum transferred from the ferromagnet to the non-magnet. Okay, and from here there will be a modulation of damping, and from the modulation of damping we can measure the spin pumping effect. So we did this experiment. Here we started with tantalum first, and again the tantalum thickness and cobalt iron boron thickness were varied. If you remember that in the spin pumping expression, both the ferromagnet and the non-magnet layer thicknesses appear. So for the modeling, we need to have the variation of damping with both the ferromagnet and the non-magnetic layer thickness. So here they remain in the beta tantalum phase for all values of thickness. And here the resistivity also shows that. So again, we did this experiment. Of course, this is the demag part, the remagnetization and the precession. And from here, we extracted the precession and measured the damping. So, and you can see frequency versus field also gives rise to all the values like MS and so on. But the damping modulation gives me alpha is proportional to 1 over D very nicely because it's linear with 1 over D. And you can see that from the modulation of damping, we can actually do the fitting with this and we can find out G effective from here. Okay, so G effective turns out to be about 7 times 10 to the 14 centimeters square. So that's a pretty large value of G effective. And now we vary the, sort of the non-magnetic layer thickness from T equals to 0 to 20 nanometer, and also measure the damping. So here delta alpha is a function of T. And if we do the, modeling of that with the relevant expression, we can see that actually it actually increases fast and then, saturate beyond that. So that is actually the spin diffusion length. Okay, as I was saying, but we can do more precise estimation from the modeling. And from here, we find out the spin diffusion length to be about 2.44 nanometer. MS, of course, is 1216 1 EMU per cc. This is the intrinsic spin mixing conductance, which is slightly higher than the effective. And this is the spin transparency. As I said, that how much spin will be effectively transported is given by the spin transparency. And for tantalum, cobalt, iron, boron, it is about 50%. It's not very high, but it's not very low as well. So we'll see that what would be the value for tungsten. But this is just to develop the technique, and that was very much appreciated, as published in Science Advances last 2 years back. And there will be other effects like spin memory loss, which is due to the loss of spin information due to spin flip scattering at the interface. And of course, the interfacial spin transparency that depends on the degree of electronic band matching that allows the conduction electron transmission. So in order to find out whether the variation in damping is purely due to the spin pumping or other effects like two-magnon scattering or spin memory loss are there, because the variation of damping will have those effects also. So in addition to spin pumping, it will also have spin memory loss and two-magnon scattering. One can do all these experiments and do a modeling. We have done that, but we have done control experiment also. We decoupled slowly the cobalt, iron, boron, and tantalum by inserting an additional spacer layer between these. So we grew a copper layer with varying thickness from 0.4 nanometer to 1 nanometer. So it's like a dusting layer. And we did the measurement of damping again. If other effects were to be present, because copper will have a large spin diffusion length. So basically the spin current will flow ballistically through copper. Okay, if it is only due to spin pumping. But if there were to be some defect mediated, two-magnon scattering, then as we increase the copper layer thickness, that will actually reduce. Or if there would be some spin memory loss, that would also reduce. But in our case, we see that alpha does not vary at all with copper layer thickness, which shows clearly that this has no effect from the spin memory loss and two-magnon scattering, and only the spin pumping is the effect which is present here. And then it was actually been appreciated by Nature India and Deccan Herald and so on. And then I did not show the the tungsten, but I just want to show that tungsten actually showed a value as high as 85%. So 85% spin transparency. And that is combined with a spin to charge conversion efficiency of 40%. So, about more than 30%, 35% spin current will actually be, spin to charge, effective spin to charge conversion will occur in tungsten and cobalt iron boron. So that's a great news for the spin orbiter effect of spin orbitronics. So now I will talk about the interfacial Zalesinski-Moria interaction. As I said, it is an asymmetric exchange interaction which occurs in material with broken inversion symmetry. And how it actually came. So in 1958, so Zalesinski actually gave rise to a phenomenological theory of antisymmetric exchange coupling between spins to explain the phenomena of weak ferromagnetism in antiferromagnetic compound. And then in the preceding years, the Moria actually derived this interaction as a spin orbit coupling between electrons within the framework of super exchange theory. And that was then known as the Zalesinski-Moria theory, and give rise to an anisotropic exchange interaction that arises in material that lack inversion symmetry, where strong spin orbit coupling effects are present. And these are generally present in non-centrosymmetric bulk ferromagnet, multiferroics, perovskites, cuprates, and also in ferromagnetic thin films and heterostructures. And they give rise to chiral spin textures, like spin spirals, magnetic helices, skyrmions, skyrmion lattice, chiral domain walls, and so on. And all of these are very important because chiral magnetism, chiral magnonics have become a very, very interesting topic recently. Because some of them are, for example, skyrmion is a topologically protected structure. So you cannot really, change its topology very easily. Okay, so but the origin of skyrmion and all these lies in the occurrence of interfacial DMI or Zalesinski-Moria interaction. So we wanted to study that. As I said, it's an antisymmetric exchange. It has a form of Tij dot Si cross Sj. So this is actually a torque-like term, as opposed to just Si dot Sj term in Heisenberg exchange. And it occurs in system with super exchange and strong spin orbit coupling. So basically, it's a three-site exchange interaction. So if you have a ferromagnet like nickel iron and a non-magnet or heavy metal like platinum, so the spins of the ferromagnet actually couple through an atom in the non-magnet. Okay, so it's a three-site exchange, and as a result, it actually generate a chirality. Okay, so if you are flowing along this direction and that direction, the chirality is different. So the spin wave, which is propagating in the positive or negative direction, will have a different effective field, but the DMI vector will have a different, direction with respect to that. And as a result, you will have different frequency or different peak intensity or different peak line width. So these actually give rise to a non-reciprocity in the spin wave propagation. Okay, and this DMI can be measured from the magnetostatic surface wave or the Demagnetization spin wave mode in its asymmetry in peak frequency, peak line width, and peak intensity, as I said. Okay, and I already said its application. So how do we measure it? We'll measure it by using the Brillouin light scattering, the inelastic light scattering, as I said before. So here we have a sample, which is tungsten, cobalt, iron, boron, silicon. We like tungsten very much because it is cheap and it has a very nice, interface with cobalt, iron, boron. And we like cobalt, iron, boron, and of course tungsten, as I say, it can give rise to a very high spin Hall effect and very nice spin transparency. So this is very important material. At the same time, cobalt, iron, boron is very important material for magnetic tunnel junctions, which are used in the magnetic RAM or MRAM devices. Okay, so here what we did, we varied the cobalt, iron, boron thickness from, actually these are swapped. So cobalt, iron, boron thickness actually was varied from 0.85 nanometer to 3 nanometer, and tungsten thickness was varied from 1 to 6 nanometer. Okay, and we varied that from the spin wave dispersion, from the asymmetry in the spin wave dispersion. And here you can clearly see that when we switch from plus k to minus k, there is an asymmetry here. Clearly, not only the intensity asymmetry, but the frequency asymmetry is also there. And this frequency asymmetry is known as delta F. And if we actually plot the full dispersion as a function of k, we see that instead of this dotted line, which is a symmetric dispersion, you have an asymmetric dispersion like that. Okay, and from here we can do this modeling using the spin wave dispersion equation, where I add this term, which is the Dzyaloshinski-Moria term, and this term is linear in k, so d plus minus k. So if I change the sign of k, so then this term will either be added or be subtracted. So as a result, the asymmetry occurs. Okay, whereas this term is primarily varying as k squared. Okay, it is k squared primarily. So the change of sign of k does not affect this term. Okay, so we did that, and we have a nice modeling, and you can see these red lines are actually a fit, which also shows the asymmetry, and from here we can find out the value of d. So we did that, and the delta f as a function of k is also plotted here, and you can see delta f can go as high as 0.4 gigahertz or something like that. And from here we can find out the Dzyaloshinski-Moria vector. So for the Heisenberg exchange, the value of J or A, the exchange stiffness constant is important, and here the value of D is important because you can see D is the strength of DMI. Okay, so this D is coming out to be about 0.25 millijoule per meter square in case of tungsten, cobalt, iron, boron. And you can see that it actually shows a very linear variation, linear scaling with the inverse of the cobalt, iron, boron thickness, which shows that it is pure, because if this were to be some, degradation or some other impurity or other things happening, then it should have deviated from the linear behavior. And previous experiments showed that it has a deviation from linear behavior even in 1 nanometer range, but here even down to 0.85 nanometer, that is sub-nanometer thickness, we do have a very linear behavior. The line width also of course it is scattering, but it also gives rise to an asymmetry, and from here we can find out the d and the alpha value. And we did the underlayer thickness variation as well. And here also we can find out the DMI, and you can see that here the delta alpha is actually increases to about a value of 0.8 gigahertz at the transition region from beta alpha to beta tungsten to alpha tungsten. And here also the value goes as high as 0.4 millijoule per meter square, which is a very high value for tungsten. So what is happening here is the lattice parameter of beta phase of tungsten is larger than the lattice parameter of alpha phase. And that can cause a difference in the position of large spin orbit coupling center, because the spin orbit coupling center is the tungsten atom. That is the non-magnetic metal. Okay. That is actually the adjacent to the, because it's a three-side exchange. So there will be two ferromagnet and one non-magnet, and that non-magnet is tungsten here, and its position is important for the spin orbit coupling strength. And the slightly different arrangement of tungsten atom in different phases of tungsten, that is beta phase or alpha phase, with respect to cobalt or iron atom, which are the ferromagnetic atom, they can result in this significantly different magnetic inhomogeneity and this DMI value. Okay, so that was that. And then finally, I come to how much time I have? Okay, I have about 20-25 minutes. So I'll come to another topic called this two-dimensional magnonic crystal. So in the previous lecture, we have been talking a lot about magnonics and correlation in photonics and so on, but magnonics has a very unique advantage over photonics, phononics, or any other NICs. Okay, in the in terms of its unique spin texture, which it's very difficult to have. Like in a magnetic dot, for example, if you are actually reducing the size, you can get different kind of domain structure. I showed you already. You can have flower state, S state, leaf state. You can single domain state. You can have vortex state, and so on. And all of them have different kind of frequency, different kind of internal field, different kind of interaction field. And magnonics are having an interaction between the elements, whereas the photonics or phononics, the elements are not interacting with each other through the any magnetic field or something like that. In their case, it is interacting through the medium. Okay, so these are the unique advantages of magnonics, and you can see how these nanomagnets interact when placed in an array will give rise to their dynamics. And we can actually change them very easily, not by changing their size or shape or anything, but also by the strength of the magnetic field, their direction, and so on. So a lot of control parameters are there actually. And of course, this thing I already explained. I do not have to explain it again. So I come to sort of some examples. So these are kind of some of the first work we do long time back. So what we did is we actually placed square dots of permalloy, which is nickel iron, which has negligible magnetocrystalline anisotropy. So the primary anisotropy will come from the shape, size, and their interaction. And what we did is we placed them in such a way that their lattice spacing is varying from a very small value, so about 50 nanometer separation, to about 400 nanometer separation. And because they interact very strongly by the dipolar and other higher order multipolar interaction, so we want to see what actually is happening. So we did the time resolved experiment on them. And these are the car rotation as a function of time and the frequency component from the Fourier transform. And these are as a function of magnetic field. And we did this modeling using Kittel equation, and we find out the parameters. And then we did the experiment as a function of the inter-element spacing. We are varying from 50 nanometer to 400 nanometer and see what is happening. So when we are at 50 nanometer, we are getting a single mode, single precessional mode. That is amazing. I'll show you why. And even at 75 nanometer, and this is the simulation. We do micromagnetic simulation. It is a full, you can say finite element or finite difference method based simulation. And it actually reproduces it completely. And even for 75 nanometer single mode, as we go to 100 nanometer, the mode actually splits and a third mode appears. So from a single mode, we go to a 3 mode. And here the mode spacings are increasing fine. And finally, when you go to about 400 nanometer, we start to see only 2 mode, even here. So what is happening? Why we are seeing such a strange variation in the mode structure? In order to understand that, we first go into their interaction field. So we calculated the interaction field. So these are, you can see magnetic field lines, internal field and the stray field. And we take line scans. So here you can clearly see that they're actually interacting not in dipolar, but a quadrupolar way. Okay. So we do take line scans and we plot them as a function of their separation. And of course, these are where the dots are there and these are their separation. So as the separation is increasing, so this region is also becoming broader. But what is happening at the field? And you can see that here, for 50 nanometer, the field value is of the order of 3 kilooerstate. So even though there is an air in between, but the field line is giving rise to a field value of 3 kilooerstate, which is very high. The applied field is only about 1 kilooerstate, so it's much higher than the applied field. And as we go to 100 nanometer and higher, this field value actually reduces drastically and goes down to nearly 0. So, but here still some field is there. So that causes the coupling. Okay. So the coupling here is extremely strong. The coupling is so strong that it is giving rise to almost a uniform like of mode here, which is not similar to the mode of individual dots. Okay. So that's what we did. So we first calculated the mode profiles of a single dot, and the single dot has a mode profile like that. So it's kind of a uniform mode of the single dot, and this is an edge mode where the mode is actually happening at the demagnetized region near the edges. Okay, so fine. But when you put them in array, what happens? That when you put them in this array with S equals to 50 nanometer, only single mode is appearing. Here you can see that this edge mode actually disappear. You have a completely uniform mode. So this is almost like as if it is a thin film. Although there is a gap between them, but they are appearing like almost like a continuous film. And that is this uniform mode of the system, strongly collective mode. It is called the strongly collective mode. And this mode will be able to propagate through this medium over a long distance. But when we come to this kind of situation, like S equals to 100, we have 3 modes. And there you can see that this mode is similar to this, the center mode. This mode is actually similar to the edge mode. In addition to that, you have another mode. And here you can see these are kind of standing wave modes, which we also call a quantized mode actually. Similar to a harmonic oscillator, this is a standing wave mode with n equals to 3. Okay. So this is a weakly collective mode. So, and when we go to 400 nanometer, we'll see only these 2 modes. So these are completely isolated. They are no way interacting with each other. So this is what we are going from a strongly collective regime through weakly collective regime to a completely isolated regime. So, and then we try to see what happens if we change the size of the dot. Of course, when we have a larger size, we have this uniform mode and also the edge mode. But as we are reducing the size, the edge mode should disappear in principle. And we should have a uniform mode because it should go into single domain. But if that is the case, so we did that, and here the size, size is 200 nanometer, sorry, this is 50 nanometer dot. We are not varying the size yet. So we are taking a 50 nanometer dot, which is much smaller. So our first goal is can we measure a very small dot as small as 50 nanometer. Okay, so here the dots were 200 nanometer. Okay, width was 200 nanometer. Here the dots are 50 nanometer, and see we are measuring by an optical technique, where the spot size itself is about 800 nanometer. So 800 nanometer, if you actually focus on here, it will have only a single dot under it. But when you slowly go to this regime, you'll still have few dots. So we'll go from a sort of multiple dot to a single dot like measurement. So question is, can we measure a single 50 nanometer dot, which is generally impossible to measure without the near field scanning optical microscopy or something. And we are measuring in the far field. Okay. And we have increased the sensitivity of the measurement in such a way that we were able to measure this. So here you can see that we are going from S equals to 15 nanometer, that is separation is 50 nanometer, which is still like you have multiple dots. And slowly you're going to 200 nanometer. And here also, like in this situation where a single dot is measured, you still have a very nice precision and damping as well. And you're able to measure these. Of course, here is mode splitting occurs. When we measure the damping, we start to see this is the frequency as a function of their width. And we can see that it can be modeled by using an expression with dipolar and quadrupolar interaction. And we see that the quadrupolar interaction is more dominant here, actually. Okay, well, the damping shows a very interesting behavior because the damping goes from a small value to sudden jump to a very high value. And this is probably due to this dynamic dephasing between this, because when you are here, it is like individual dot behavior. And slowly when you are going to this kind of regime, here the dots are precessing and they have a slightly different shape and size. So their frequencies will be slightly different. So they can give rise to an inhomogeneous line broadening and a dephasing. Okay, and that can give rise to a large value of the damping. Here we show the variation is in the size. So you can see the dot size, 200 nanometer, you have 3 different modes. And as we go to region 2, that is about 100 nanometer, it goes to a single dot. And when you go to 50 nanometer regime, you have a single mode. So 3 mode to 2 mode to a single mode. But I said that a single dot of 50 nanometer should be a single domain. So it should have a uniform mode of precision. But instead, it has an edge mode. So the edge demagnetized region is so high in this case, so the uniform mode actually disappears here. So this is a new finding. And these papers were actually published here, like SCS Nano and all these journals, all this work. And here I show in a more better way that if I take for this 400 nanometer, I say 200 nanometer separation, and take one of the dot here, zoom it, we find that they have a only edge mode. There is no, uniform mode here. So then we thought that what will happen if I vary their shape. So we actually prepared this kind of structure from circular dot to half ellipse, rectangular dot, diamond, and triangular dot. And all these dots have kind of non-ellipsoidal shapes. So they cannot be explained by an uniform mode, like we showed that for an ellipsoid, we can have a uniform mode. And so they will have very strange kind of spin texture and very non-uniform internal field and, sort of the stray field. So really what happens here, we did this measurement and these are the spectra. And you can see that they go from nearly a single mode to 3 mode. And finally, for the triangle, the diamond also, they have a 3 mode. For a triangle, they have like 8 modes. So the same material, same size, only the shape is different. And that can change their dynamics by a huge amount. They go from a single mode to 8 mode. Okay. And what happens here is we do their mode profile analysis, and we see that from a uniform mode, you can go to here, for example, there are various kind of hybrid modes. Here, these are backward volume standing wave modes with different mode numbers, like n equals to 3, 5, 7, and so on. And here you have hybrid modes of backward volume modes and demonstrate. And we can calculate their mode numbers and characterize them. Interesting thing is that all these modes, for example, if I want to prepare a filter, for example, okay, then I can have this kind of structure with a circular dot. I can only, filter out this. And if I want to propagate a large number band of mode, I can have a structure, triangular structure. Okay, I can also have hybrid kind of structure where I can mix up this different kind of structure and start with this, and slowly one by one I reduce the different band and go to a single band. So this can act as a filter or mode selector or different kinds of magnetic devices. And then we want to see, because we are working on artificial crystals, so the lattice symmetry is also important. So what we did is we took the circular dot, because we know the circular dot generally give rise to almost a single mode, okay, or maybe two modes. So if I place them in different kinds of lattice, what happens? Here, I see that, and so far I did not vary their bias field orientation. I'm only showing you for a single bias field orientation. Okay, and here we have prepared them in square lattice, rectangular lattice, hexagonal, honeycomb, and octagonal lattice. Okay, octagonal lattice, of course, a non-Bravais lattice. Honeycomb can be a Bravais lattice with 2 atom basis. Okay, but if you consider single atom, then it is a non-Bravais, and these are, of course, the Bravais lattice. And here the modes, and you can see from a single mode behavior for square lattice, it enters into for a honeycomb lattice, it has 6 modes, and for octagonal it has 3 modes. So just by varying this, we can vary the mode localization behavior and the collective precessional behavior. Okay, and if I now rotate the magnetic field, this is the bias magnetic field orientation. So if I rotate the field, I see the it goes from a 4-fold symmetry with a 2-fold symmetry and up to 8-fold symmetry, with 6-fold, 8-fold symmetry. And you know that 8-fold symmetry is generally not possible in a crystal, normal crystal. It is possible, this higher order rotational symmetry is possible only in quasi-crystal. So these are actually behaving, this octagonal lattice behaving like a quasi-crystal. We're not fully utilizing its behavior here now, but in other work we had done that. I don't know whether I have time to show that, but I want to show that how the collective precessional behavior change from here to here. So here you have 2 modes, a single mode behavior, you have 2 modes, and you have multiple modes, and you can see the mode profiles are very different. Their collective power, here the power is distributed uniformly, here power is distributed at the center, and if you look into the phase have kind of an alternative change kind of behavior. And here there's a bow tie kind of mode where it's forming a bow tie like behavior and so on. And for the non-Bravais, the honeycomb and octagonal, they have even more complicated phase and power properties that we have completely characterized. I'm not giving you the details here. Just have a look. And if I calculate their sort of the stray field distribution, and you can see how they're sort of interacting here. The interaction is very strong. You can see interaction is becoming weaker. Here you can see the interaction is very localized. So you have different kind. Here is strong interaction, here weak interaction, and so on, because these are kind of, so basically you cannot complete the tiling of this hexagonal and honeycomb by a single kind of tile, but you need to have this kind of rhombic tiling as well. So as a result, the rhombic region has a different internal field profile, where this octagonal or honeycomb has a different internal field profile, and so on. And we did this internal field analysis as well to understand the mode behavior and so on. So finally, I think I have, if I have 5 minutes left, I do have many more slides, but I don't have time to show that. I show that how we can use the ferromagnetic resonance. So far, we are measuring it by time resolved MOKE. Here we have used ferromagnetic resonance. So here you can see we can do a series of measurement at different fields, and we can plot them. And all these white regions are actually a peak. Okay, so you can understand how many, like more than hundreds of spectra are plotted together to find out this. So this is for a single, continuous film. And when we have this kind of, different shape of the sample, so they will have different kind of behavior. So for circular dot, you can see that at a high field, we have a single mode, but when you are reducing the field to a low field, they show beautiful mode splitting. And you can see 3 modes are appearing here. Square dot, it is nearly like a 2 modes always. For the diamond dots, you can see there are 3 modes, and this mode is more prominent. The top 2 modes are not so prominent. And triangular dot here, only 2 or 3 modes you can see very clearly, but the modes which were appearing here, here you can see for a triangular dot, these 8 modes, they cannot be found in the ferromagnetic resonance. So you can now compare between the electrical detection and the optical detection. One can say that these are very strongly coupled. Maybe that is the reason that you have a, uniform collective mode, or more or less weakly collective and strongly collective modes are there. But the difference between the electrical and optical measurements can also be seen from here. And here we can do the field variation and the bias field orientation variation. And you can see it goes from a 2, 4, 2 plus 4, here 4, 4, and 2 plus 4. And finally, you have 6, 4, 6 plus 4 plus 2, different kinds of rotational symmetry you can observe from this measurement. Okay, and these antidots, I want to show at least one example of an antidot, where instead of this kind of dot, we actually mill holes in the film, continuous film, and by using focused ion beam milling. And this go down to 100 nanometer, which is very difficult to make actually. I'm not giving you the details of that. So one of my colleague, Kaustubh Das, he actually helped me to prepare this by using this. And we can see that we actually changed their lattice constant, lattice parameter. And here you can see that we go from 2 modes with a single band gap to increasing band gap. Just by changing the lattice parameter, we can increase the band gap and finally creating four bands. And the reason behind those can also be seen. This is the mode profile. You can see that you have a continuous mode, and then you also have this kind of quantized modes, and their behavior is changing drastically as a function of this lattice parameter. So with that, I will sort of show that here also you can do the shape variation and so on, and you can also develop bicomponent. So because these are crystal, you can also have an alloy. So here we have prepared cobalt iron boron nickel iron. So this is kind of bicomponent. So in an antidot, we filled it with another material. So the preparation is not so easy, very difficult, and we are able to show that how the bicomponent behave, how their propagation actually occurs there. And finally, we did this voltage controlled magnetic nanochannel by using something called voltage controlled magnetic anisotropy, but I do not want to describe this. But if you are interested, you can read this very recent paper in Science Advances, where we actually developed some device using voltage controlled anisotropy. So fine, thank you. This is my group. I thank them all for their contribution. And these 2 primary collaborators, this person is from Chemnitz and HZDR in Germany, who gave me samples for this demagnetization measurement, and some of these dot and antidot arrays were given by this, and some we prepared by ourselves. And these are 2 sort of book and book chapter. You can have a look if you're interested in spin dynamics. And these 2 actually Magnonics roadmap, actually I was selected to act as an editor and lead author of this Magnonics roadmap, which also appeared recently. And this is a perspective article, but also many thing about spin dynamics or magnetization dynamics will be available. So thank you very much.
Thank you, sir, for your nice, exciting talks. So session is already open for your question answer. If you have any question, you can ask Dr. Barman. He is ready to answer your question. I also share feedback link as well as your test link in your chat box. Please give your feedback as well as give your test. In the meantime, you can ask the question to Professor Barman. Please, you can ask. If you have any question, please ask.
If you have questions, you can also send me by email.
Sir, email ID is not there. Okay, I can share you sir email ID.
Sure, sure.
Yeah, so if you have any problem, question, you can mail him also directly.
You can ask here also.
Yeah, definitely you can ask here.
Because I cannot see the chat box. So if there is any chat question in the
Oh, the chat box, no questions are there. Mostly my messages from me, sir.
Okay, okay.
Yes, Dr. Acharya, please ask.
Sir, I'm Devanjan Acharya, sir.
Yeah.
Am I audible?
Yeah, you are audible.
Sir, I have a query regarding the transistor, the MOSFET transistor. It plays the existing conventional structure with the magnetomics. So, what will be the figure of merit for that? I mean, what is the figure of merit for the development of such kind of transistors? Like spintronics, we are already, kind of developed, not developed. It's already research has already been done some up to some extent. But if we go for the magnetomics-based transistor, then what will be the figure of merits for that? The basic figure of merits.
I think the basic figure of merit will, of course, with the output current and, so here it is magnon current and primarily the gain. Okay, so we have done work on magnetic vortex transistor in the last in the last lecture I showed you, and we are continuously trying to increase the gain parameter. And there is some magnon transistor also. People are trying to increase the gain parameter, and the other things like standard transistor, bipolar transistor do. So the research is up till now up here, and people are also trying to develop fan in and fan out operation and so on, so that you can transport the signal over a large circuit and so on. So far the research has progressed up to this much. Okay. But of course, much more has to be done in order to be parallel to electronics.
Thank you.
Sir, I have a question.
Yes,
sir, what is the future of MRAM? As you may know, there are in the competition, exchange memory as well as memory star is there. So which one is the best at this stage?
See, as you know that MRAM is making a lot of development recently because of the spin orbit torque, and this SOT MRAM will soon start to produce few gigabytes.
Yes, sir.
Right now 2 GB SOT MRAM is being developed by Everspin. It will go up to several gigabytes and so on. But because it is non-volatile and it is very fast, of course, because the switching can be very fast, of the order of picosecond, and it can probably be gone down to femtosecond if you can do optical writing and optical reading. So and it can be small, and it can be easily integrated with the magnetic system. Like you already have the hard disk, magnetic hard disk, and all this. So that way, MRAM, SOT MRAM will have a great future. And
yes,
at the same time, this spin logic and other spin processing and spin communication technology also has a great future, but they have to be sort of integrated with the the other devices. So the integration part is not easy. So that is sort of, I would not say it is an advanced technology, and the technology actually started only 10 or 12 years back. The magnonics started, it's a very young technology. Although the ideas were there, it only started in 2010 or something like that.
Yes.
So it's only 10 years old. So, but it has done a lot of progress. So, and because it has its intrinsic, properties, like I was showing, because of its intrinsic anisotropy, miniaturization, easily, reconfiguration, that is very important. That this is reconfigurable and reprogrammable very easily, but just by small change in the magnetic field and so on, or current or so on, and non-reciprocity and various other properties. So if you are interested, you can read this roadmap. It has come out in Journal of Physics Condensed Matter. Yes. It has been written by about 60 authors. It has 22
yes, I saw this paper.
So if you read this paper, at least if you read the introduction, which I have written by combining all the things, so you will have some idea that where magnonics is going in next few years. Okay.
Sir,
so
sir, another question is that MRAM only applicable for non-volatile memory, or is there any other applications are there for MRAM?
No, I mean, wherever you want any memory, I mean, it's non-volatile. That is its intrinsic property. I mean, not only in computer, in other parts also you can. People are also using it in as various memory device in in a car for sensing and other things also. Like I have student who had done PhD in magnetics, and now he's working in Germany in some car company, and they are preparing a lot of sensors and various other devices using this GMR and MRAM devices. Okay, so there are multiple applications.
So, any other questions from participants?
Good evening, sir.
Yes, please.
Sir, you have just done a good presentation and laborious work over there. To understand, it'll take a lot of time. So I just have some basic doubts on magnetism. So shall I ask regarding this?
Yeah.
Yes,
Go ahead.
please.
Actually, I just have a doubt on the hysteresis. So every hysteresis shows some smooth curve. So I just have a doubt that if there are multiple domains with different shapes are there, each and every domain will try to contribute a magnetic field in a different strength. Why this should not combine together to form a thing? I just want to just clarity that whether there may be a different domains with different magnetization property combined together to show a hysteresis. Is there any possibility like that, sir?
Look, when you are measuring hysteresis, you are measuring the average, right?
Okay.
Average from all domains. So if you are doing a local measurement, for example, if you can do measurement from say individual domain, or if you can do a sort of image the domains, and you can measure from individual domain, you will get different hysteresis loop. Okay, but if you are doing an average measurement, you will get an average behavior of that. So when you have domain, if you remember, maybe I go back a little bit. I don't know if it is working. Somehow, oh yeah. I mean, in some of my previous slides. Luckily, I have, here you can see. So here I have same material with varying thickness. So this is a square loop. So here you can see it is actually having a coherent rotation. And in some of my in the previous lecture, I showed you that when you have coherent rotation or domain formation or curling mode, buckling mode, and so on. So when you have a square loop, it is coherent rotation. All the domains, whether generally there is no domain, it is going from a up state to down state, just a coherent rotation. It just crosses the anisotropy barrier. But when you come to here, so this loop, you can see, it has a very strange kind of behavior. So this actually shows that it's formation of stripe domains. So various stripe-like domains will form here. Okay, and here you can see a domain which is like almost like a continuous variation. So here you have multi-domains. So as individual domains are switching, slowly, it is actually switching gradually. Okay, in some cases, if you actually, zoom on this, you'll see small steps. Okay, so those can actually, be considered as switching of the individual domains or individual part of the sample, and so. So, and this is only 2-3 types of hysteresis. There can be a number of hysteresis types of hysteresis loop shape, from where you can actually do a lot of analysis. And we do not just, study the hysteresis as like this. We also study what is happening, how the magnetization reversal is occurring. I have not showed you here, but we do a lot of work on that also. The different reversal modes we actually study.
One more doubt, sir. If we want to just study about the magnetic behavior for multiple domains, same material, okay, for example, nickel cobalt, if we just take, so same material, they may, because when you just go bulk growth, so you are very precisely growing at a particular thickness.
Yeah.
So where you are just getting a very perfect square loop.
Right.
But when you just go for bulk deposition like thick films, when you go for it, there may be some multiple domains. So
Yeah,
when
yeah.
you go for modeling, which method will be very emphasizing to do it so, sir?
Now, even for multi-domain thick films, anything, you should model by using finite element or finite difference method-based micromagnetic simulations,
Okay.
because it is a continuum model. If you cannot do modeling of this kind of structure using discrete spin model like Ising model or something, that will not work. In electronic structure calculation like thing will also not work. The only model will work because you have a large sample is the sort of micromagnetic simulation, and there are various kinds of micromagnetic simulator or solver.
Okay.
By using those, you can actually be able to precisely, even my son can do it. Okay,
Okay.
so it's not difficult. If you learn that, and if you understand this physics a little bit, you can do that. Okay.
Okay. Thank you, sir.
Thank you, sir. I
Okay,
think
thank you so
there
much.
are no more questions, I think. So I like
Okay.
to tell you all the participants one important hidden thing of Professor Barman. He is a very good poet. So he wrote lot of books, lot of poetry books. Anyway,
Thank you.
so I like to request Dr. Demagnetization to give vote of thanks for Professor Barman for giving his excellent talk for students and give us a lot of light on the magnetism. So, Dr. Acharya, please, you can just speak the vote of thanks and we will come.
Thank you, Dr. Panda. Am I audible?
Yes, yes.
Thank you, Dr. Panda. It's my great privilege to give the vote of thanks to the stalwart researcher like Professor Barman. I am Dr. Devanjan Acharya, working as assistant professor at IIT Ranchi. From the very first lecture, Dr. Barman has taught us different, starting with the very basic of the electromagnetism, magnetics to the magnetics, and I can quite sure that the participant has enriched with the knowledge of different dimension of the magnetics, like the crystal dimensional magnetics for different quantum dots, quasi-crystal, then the spin orbit effects, then some damping factor, and the some sir has also told about the transistor which is basically depends on which is basically working on the principle of the magnetics. And not only that, there are several things we have learned, from the very basic things towards the very complicated and the cutting edge research arena regarding we have also learned those things. Not only this, you can go with the permission of Professor Barman. I can suggest you that the sir with the paper the sir told about the roadmap of the magnetics is a very well written and very well organized research paper. I have also gone through this, and it's a very kind of thing. So you will get an idea about this. Who don't know about the magnetics, you can easily understand the things what are to be going on. It's a kind of things I can compare this thing with Murray's law, which are popularly known in kind of the roadmap for the electronics. And this the paper that went the 2021 magnetics roadmap, which is published on the Journal of Physics Condensed Matter, is also that kind of things we can get an idea about the roadmap of this field. And thank you very much, Dr. Barman. We look forward for more this kind of lecture from you, and we will look forward. And one of the last, not but the least, that is the thing, the indigenous lab developed by the Professor Barman is it's very interesting and very lucrative one. That because the most of the things the researchers are going for the purchasing the thing, but it's very inspiring for a young people like me that he developed his own experimental setup. We will always look forward if Professor Barman allow us to do some experiment in this field. So thank you, Professor Barman, and thank you very much for the participant, and thank you all. Thank you very much.
Yeah, thank you so much, Professor Panda, Professor Acharya, and then all the participants. And as you said that, yeah, of course, right now, because of pandemic, we are also, everything is kind of closed, but when things actually become normal, all of you will be very much welcome and warmly invited to our institute and have a visit to our labs and, discussion about research and so on. We actually do organize such, visits from different universities, colleges, and students, even schools students. So kind of like open day. So on Science Day, we do that, or other days also we do that. So you're all welcome to visit our lab and have a look around. Thank you so much.